Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to continue to go over periodic trends, and we're going to go over ionization energy in this video. Okay, let's get into this. So, periodic trends. So again, it all goes back to the trend in effective nuclear charge. What's happening in the nucleus? Is it getting bigger? What's happening with shielding? Is there shielding going on? What's happening to energy levels? Are we adding energy levels? Things like that. And it always goes back to Coulomb's law as well. Remember, so as electrons get farther from the nucleus, there's a not as strong of a pull on those electrons. The bigger the charge, right? Bigger charges have stronger pulls on each other. And so that's going to be the factors that we want to think about when we're thinking about periodic trends. And so right now on the board I have here so the periodic table. And so here are the groups. It's kind of weird, but that's the way it is with my drawing. So we have this group 3, group 4, 5, 6, and so on. I don't have 7 and 8 because of lack of room. And then I have 3 periods, or at least 2 periods, and then I have potassium in the third period. So when we're looking at ionization energy, we have to understand that what ionization energy is. So ionization energy is the energy required to remove one electron from a neutral atom. So we're removing the first electron from a neutral atom. How much energy does that take? Okay, so we got to think about is it is it going to be easier or harder to take an electron away from an atom if the nucleus has a larger charge, right? So if the charge in the nucleus is larger and the electrons are feeling a larger pull, a larger attractive force by the nucleus, then it's going to be harder to remove that electron, and it's going to take more energy, right? So therefore, we would expect that the stronger the pull on the electron, right? The stronger the pull, the stronger the attractive force on the electron, the harder it is to remove that electron from the atom, and therefore we're going to need to put more energy in. So more energy required. Okay, so there are two factors that affect the pull on the electron. The first factor is the size of the charge, right? And when we're thinking about size of charges, we're thinking about the nucleus. So more charge in the nucleus means more pull. And also we need to take into shielding effect as well, because some of that shielding is going to counteract some of that size of the charge. That's why we need to look at effective nuclear charge, because the effective nuclear charge takes in consideration the shielding effect. And so we can look at the effective nuclear charge and say, okay, is the effective nuclear charge large or small? If the effective nuclear charge is large, then that means greater attractive force, which means that you're going to need more energy to remove the electron, therefore higher ionization energy. Okay. The other thing we want to look at is how far the electrons are from the nucleus. So remember, distance matters if we're thinking about Coulomb's law, right? So the closer the charges are, the stronger the attractive force. The farther those charges get away from each other, the weaker the attractive force, right? So again, if the attractive force is weaker, it's easier to take away the electron. It doesn't take as much energy. So less energy means less ionization energy. So those are the things we want to keep in mind. So let's look at our periodic table. Let's look at the effective charge. Let's look at the size of the atom, right? So if we can remember what's happening with the size of the atom and why, then we can remember the ionization energy. So we saw with the size of the atom that as you go across, the size of the atom decreases. Why? Because the effective nuclear charge is increasing. So what does that mean? So the larger the charge, the more attractive force, the more it's going to pull the electrons in. So therefore, the electrons are feeling a greater force as you go across the periodic table. So this electron here is not feeling as much of an attractive force as this electron. So if this electron is only feeling an effective force of 1, a +1 charge, then this one will be easier to remove because it's not held as strongly. This one has a larger attractive force, so it's got an effective nuclear charge of +2, so it's feeling a stronger pull, and therefore it's going to require more energy to remove this electron from this atom than it does this atom, and so on. So these electrons feel an effective force of a +3. So removing one of these electrons is going to require more energy because they feel a greater force, and so on. So because the effective nuclear charge is increasing going across the periodic table, therefore, we would expect the ionization energy to also increase. So the amount of energy required to remove the electron should increase as well because the electrons are feeling a greater attractive force, and so it's going to be harder to remove that electron, which means it requires more energy. Okay, what about going down the group? We saw before that going down a group, the effective nuclear charge pretty much stays the same. And again, the reason it stays the same is because although the nuclear charge is getting larger, so is the shielding. So the shielding is increasing as well, so they counteract each other. So the effective nuclear charge is pretty much the same, +1. So the attractive force of the nucleus on the electron is not changing all that much. It does change, but what we definitely notice here is as you go down, you're adding a larger shell. So the valence electron is getting farther from the positive nucleus. And so because that valence electron is getting farther from the positive nucleus, that positive nucleus is not able to attract the electron as strongly if it was closer. Because remember, as the electron gets farther from the nucleus, that attractive force decreases. So this electron here, we would expect to have a stronger force on it, and therefore removing this electron would be harder and therefore require more energy, therefore more ionization energy than, say, this one here, because it's farther away. So this electron is farther from the nucleus, so this would be not as strongly attracted, so it would be easier to take this electron away. And therefore, it would be easier to take this electron away because it's even farther from the nucleus. So we would expect that the ionization energy, the amount of energy needed to take the electron away, would decrease going down a group because you're getting farther from the nucleus. And again, farther from the nucleus means weaker attractive force, easier to remove the electron. And so going back to my periodic table here, we could write the trend as follows. So as you are going across the periodic table this way, then ionization energy increases, right? So i.e. ionization energy increases going across, and it also increases going up a group, or it decreases going down a group. Either way you want to think about it. So ionization energy increases going up the group. So then the overall pattern in the periodic table is that going from this corner to this corner, you have increasing ionization energy. And that's the pattern. And so we can see that we can understand this pattern, we can remember this pattern here, this trend in the periodic table with regard to ionization energy, because we understand the trend going on with the effective nuclear charge and shielding, and what's going on with the sizes of the atom because of that. So when we're going down a group, we're adding energy levels. Electrons are getting farther away. As we go across a period, the effective nuclear charge is increasing, pulling electrons in closer, more strongly. And so you could see how the trend of atomic size or radius is matching or related to ionization energy as well. So if you can remember the trend of size, then it's easy to remember the trend for ionization energy, because they're both based on the same things, which is effective nuclear charge and distance from the nucleus. I hope this was helpful. If you like this video, please smash that like button. Please subscribe to my channel. Hit that notification bell so you can be notified by other videos I put out. Put a comment in the comment section. Let me know what you think and if you have any questions. Thanks for joining me. Have a great day.